record here. And 13. Okay, then let me come over here and share my screen, and then we'll work through this problem. Oh. Oh, hey, it's interesting. Oh, okay. I did notice that my phone looks like it updated to whatever the latest version was, 15 something.
Oh yeah, iOS 15.
Yeah, but when I go to the normal share screen, it changed. It has a little thing called focus. That was interesting. But then right next to it, they had, and I guessed right. It looked like a share screen. It had like two screens interlapped with each other. And I go, well, let me hit that one. So I sure you know what I'm talking about. It's just like all of a sudden a new version, they move things around and you're like, uh-oh.
Yeah.
Panic time. I was like, uh-oh, how do I share my screen here? All right, but it looks like I found it here. Okay, so with that in mind, let me switch back over here to the questions. And number 42, I'll read it here. It says a battery has an EMF of 9.2 volts. So maybe I'll start there and make where the chemical reaction would be. So here's 9.2 volts. And then an internal resistance. And so inside of it, just because of the way it's built, not that there's actually one put inside of it, we'd like that to be small, but let's just say this is a lead acid battery. You got to have the plates and you got to have the liquid anyways, and the electrons got to move through there, and there's some opposition, some resistance. So all that is part of the construction to make the chemical reaction. So they're saying that is worth, where'd I put it here, 1.2. To help me, I always kind of like to put a little box around it and say, okay, this is the battery. And see, you mentioned the terminal voltage, and I don't know if, and you could do it with terminal voltage, but at the same time, you could just treat the resistor as part of the piece of the circuit and never have to really focus on the terminal voltage. Now, let me explain. So then we're going to hook it up to something. And just for the sake of discussion, I'll say it's a small light bulb here. Okay. And I think that's the question. What's that resistance? So A says, what resistance across the battery, so this is what they mean by across the battery, hooked to the battery, will extract a power. So we want this power here to be 12.8 watts. So we're going to run something. Again, I'll just say a light bulb at 12.8 watts. So if you use, and I'm not sure how many or of all of the different formulas for power you've memorized, but I guess I would encourage all three of them. The standard and basic one is current times voltage. But when you apply Ohm's law to it, depending on how you apply Ohm's law, you can get this one or this one. And these are all nice because notice that the three formulas are each missing one of the variables. And so if that variable is not known and not needed, that would be the one to work with. So here we have a situation where we would like to find current. No, sorry. We'd like to find resistance. Oh, I see. I see now what you're getting at. Yeah. Seemed like it was a little bit easy at first, and then they maybe not so easy. All right.
Yeah. That's what I saw. I was like, uh-oh.
Yeah. Okay. So let me do this. Let me do a Kirchhoff's loop for this battery. So starting here, it would be 9.2 volts minus, if I'm walking around in a clockwise direction and defining the current in a clockwise direction, there would be a minus 1.2, that's the resistance times the current. Then as we come around over here, there'd be another minus I, and then that's the part we don't know, R equals 0. And so this equation, of course, has two unknowns in it. So by itself, you can't solve it. It has current and resistance. So let me use that up here with the idea of the power. The 12.8 watts should equal the current in this load resistor squared times the resistance. Let me put a little block around that. And so I would say, I guess I'm kind of done with the physics part of this problem. Now I have two equations, two unknowns. And it doesn't really matter how we solve them. But since we are asked to get to resistance, why don't I do this? Why don't I solve this first one for currents and see where that gets me? I'll put it into here, and then I would have an equation that just has resistance in it. All right, so this 9.2 equals, and I'm going to just bring these other two to the other side. And as I bring them to the other side, I'll also factor out I, so that this becomes I times the 1.2 plus R. And then, of course, solving this for just currents by itself, I would get this. So then taking my second equation, which is current squared at 9.2 over 1.2 plus R squared times R, would then be like combining of my two equations. And now I have my one unknown. So let me grab my calculator here and maybe do a little bit of mathematics. Maybe I'll start by just taking this 1.2 plus R squared and bringing it to the other side. I'll leave the 12.8 alone for a moment. It's the 9.2 squared. I thought I would do a little calculation. So that's 84.64, and then times R. Then I guess if I divide that by the 12.8, I get 6.6125 R equals this 1.2 plus R squared. It looks like it's a quadratic equation. All right, so let me square this. This would be the 1.2 squared. That's essentially 12 squared, right? Then plus 2AB plus B squared. So there's our A plus B squared from our algebra class. This is the 6.6125 R. Now, if we rearrange this so it looks like your standard quadratic equation from a math class, I'll put the higher power first. So there's R squared. Let me take the 2.4 R and subtract 6.6125, giving me a negative 4.21 R. Plus 1.44 equals 0. I'll call that page 1 and put it on here with page 2. Then, of course, the math is a quadratic equation, so R could be, and the opposite of B would be 4.21 plus or minus, and then B squared would be 4.21 squared minus 4 times A times C all over 2A. Okay, so maybe I'll do the square root here first. 4.21 squared minus 4 times 1 times 4.1. And taking the square root of that, looks like I have a 4.21 plus or minus 3. Oh, this will be fun to talk about. There's two answers. Okay, 3.46 over 2. So one option would be the 4.21 plus 3.46 and then divide by 2. So that's the bigger one, 3.835. The other one would be the 4.21 minus 3.46 divided by 2. And that would be the 0.375. These would each be ohms. So there's two answers, and perhaps not a surprise, although maybe I will look here at the solution just to double check. What was this number? 42. 3.84. Okay, good. And good. And so yeah, they got the two of them. Now they don't say much more about it, but I'm going to take a moment to say a little bit because this fits in with the first section of this chapter. It was called the energy transfer theorem, or the maximum energy transfer theorem. And basically it said if you made a plot of how much power you were trying to deliver to, I'll come back to the drawing, this external load, if your resistance is on the low end of the scale, so I'll plot resistance, and it's over here. In fact, if the resistance was 0, you wouldn't have any power. And what would end up happening, it would be like just taking a metal wire and connecting it from one end of the battery to the other. And so you would get gobs of current flowing through here. And of course, that would heat the internal resistance, which would heat the battery, but it's not giving any of its power to something external to the battery. And I guess you're not in a good design in the sense that you're not using the power from the battery to do anything other than warming the battery itself. And that's not really what you want a battery to do, unless you do want to make heat. I suppose there's a rare exception to that. But anyways, would be a short circuit. And so this could end up being, a lot of current, and therefore a lot of heat, but it's all inside the battery. It's not external. So as you then increase the resistance, you get more and more power in here. But at some point, the resistance starts to become so much that it has a diminishing return on the current. So you get less current. So, because remember, the power here is a combination of both the current and the voltage. And so if this resistance gets really, really, really high, you still get little or no power. In fact, that would be what you might say when your battery is just in storage, when you're not using it. You would say you have the resistance really, really high, and the battery, is slowly working its way through the air. But, you're talking about a resistance of probably hundreds of mega ohms. So the battery is going to last months, maybe even years, as it sits here on the shelf. And it's just not delivering much energy. Anyways, so this maximum power transfers occurs when your load resistor has the same value as your internal resistor. So in this case, if we wanted to get the most power we could out of this battery, we would hook up a load of 1.2. Now, it sounds like this power, which was what was the power for this problem? 12.8 watts is somewhere a little below this maximum. So there would be a solution below 1.2, and there would be a solution above 1.2. And that's what we found. We found the one above at 3.84 ohms and the one below at 0.375. And so both of those would work for a solution. They certainly aren't identical, so I'd be careful there. The one that's below is usually not a good solution to a problem like this when it comes to practicality, because if you're below this, well, what that means is you're actually delivering more power to the internal resistance of the battery and you're drawing a lot of current. So what ends up happening is your battery doesn't last very long. And so if the goal here was to run this external resistor, again, say a light bulb, a secondary effect would be how long could I run? And so anytime you get involved with engineering, you have parameters, you have goals, you have your primary goal and your secondary goal. And in this case, the primary goal, would be to run the light bulb. So in that case, either of those resistances would work. But criteria number 2 might be how best to run the light bulb, meaning how long can we run the light bulb, and also not risk a fire by heating up our battery. And so this solution is probably a poor one. Your battery's not going to last very long, and it's going to get warm and risk of heating things up and causing problems. So this is the solution you'd want to go to in this particular stake. But anyways, hope I didn't say too much. I'm just babbling along there, but it's kind of gives a little deeper insight to this maximum power transfer theorem, and maybe a little deeper insight into why there are 2 solutions. One of them is a solution where your power is more voltage, less current, and the other one is more current, less voltage. And that's why you have these 2, because there's these 2 factors. All right, well, there's more to the problem, so I better stay focused on it. Let me come back to the wording here. That was part A, right? What resistance across the battery would extract a power of 12.8 watts? Okay, so then B, a power of, 21.2 watts. All right, so it's really the same question. And even though I haven't done it, I wonder if the 21 is above the maximum power theorem. And they want you to kind of discover that. But let's see. Let's just start with the easy part here. Let's repeat what we just did by coming back to these 2 equations. So this first equation is Kirchhoff's loop, 9.2 minus 1.2i. By the way, this problem got far more interesting than I thought it was. This was good. Glad you asked this one. I see now why you asked it, because it just seemed like a pretty straightforward one. But it's much more interesting. Okay, so this won't change, but the other equation will. And so the current squared times the resistance now would be 21.2. And so if you'll kind of just let me use this same equation and put them together, I would have the 21.2 here equals, and in place of the current, I would have the 9.2 over 1.2 plus r squared times r. And of course, this step here, 1.2 plus r squared times 21.2. And so that'd be the equivalent of this step. But again, I would have a different number here. This would still be the 9.2 squared. So I'm still going to write that as 84.64 R. And then here's where math gets a little different. So I'll grab my calculator and taking this 84.64 and now divide it by 21.2. And I get 3.99 R. And then over here is still the 1.44 plus 2.4 R plus R squared. Is that A squared plus 2AB plus B squared? Okay. And then writing out the math as R squared. And then over here now, I guess I would have 2.4 minus 3.99, which is negative 1.59 R. That'd be those two. And then plus 1.44 equals 0. And so R would be our two answers, 1.59 plus or minus the opposite of B. And then it would be B squared, 1.59 squared minus 4AC. This is going to be the interesting part. And I'm wondering about this calculation right here. All over 2A. And then moving on to page 3. Let's see what I get here. Because I'm wondering if underneath that square root sign, we don't get a negative number. 1.59 squared minus 4 times 1 times 1.44. We do. And that would then be a negative 3.23. Now, obviously, mathematically, at least in terms of real numbers, you can't take the square root of a negative number. Maybe just for the fun of it, I will write it in complex numbers, but this would be 1.79i, okay? And basically what we're saying here is there is no real solution. There is no real numbers that can make this happen. That's why I was saying back on my graph here, under the maximum power transfer, there is some maximum power. And apparently it is below the 21.2. 21.2 is up here somewhere. There is no solution. There is no way to get 21.2 watts out of this battery, no matter what value of resistor you put here for the load. Because once you get to the 1.2, the resistance starts, if you started with a low resistance and increased it, once you get to 1.2, that's the most power you can get, and then it begins to drop off. There is no value that you can give you enough current and voltage. It would be like saying, it would have been obvious if they said, what resistor would give you 100 megawatts? You go, well, I can't get 100 megawatts out of one little battery. Yeah, you're right. You can't. But for that matter, you can't even get 21.2 out of this battery too. And that doesn't sound like an overwhelming number. So you might think you could have. But the answer is nothing would work. And in fact, if we did something like this, since we know the maximum power transfer is when the load resistor is 1.2, we could then say that the current would be this 9, where'd it go here? 9.2 divided by 1.2 plus 1.2. So let's see what that is. 9.2 divided by, that'd be a 2.4. And so the most current you can get is 3.83. So if I do I squared R for the maximum power, this is the I, so I'll square it, times the R of 1.2, it looks like the 17.6 watts is the maximum power we can get from this. So coming back to this graph, 17.6 is this peak right here. And so any question that said, can you get 18 watts or 19 watts or 21 watts or 100,000 watts? The answer is no. The maximum you're going to get out of this battery is 17.6 watts. And that's when you have a load resistor of 1.2. Just can't happen otherwise. And be curious how the author puts it in the solution B. He says, the equation for the load resistor yields a complex number. So there is no resistance that would extract a 21.2 watts from this battery. Oh, then he goes on, good. So according to the maximum power transfer theorem, you would get, and then he puts the 17.6 watts. Yeah, good way of saying it. Yeah, good. Hope that helps.
It did. Thank you.
Mm-hmm. Now that's good. Let me put that one down here. Yeah, that would turn out to be quite interesting. Oh, good. Hey, Brendan, good. Ethan, I'm going to get to yours, Brendan, but Ethan, you just asked about help with graphical analysis.
Yes, that's correct.
Do you have a specific question, or was it getting to graphical analysis?
It was with the axes. So like with
Okay.
for like a different type of curve, I guess, if that makes sense.
Okay, so can you be more specific, and I'll.
So like in one of the labs,
Yeah.
you asked to change one of the axes so that it's, I guess in your words, it was like a complicated axis for a simple output graph.
Oh yeah. I like those words. Okay.
And
yeah.
I didn't really know how to change the axes for that.
Oh yeah. Okay. So, do you remember what it was that we were graphing?
It was I believe the charge. Oh no, it was the distance with the electric fields.
Okay. Oh, actually, let me write this down. Graphical analysis. Question. Yeah. Let me get a clean piece of paper here and see if I can kind of show you on the screen here if you can see it. So, have you already in the table calculated that column for that complicated? What I'll call
I think so.
Okay, because that's step number one. So step number one, let for the sake of discussion, I'll keep it this way. Let's say that I'm making X and Y, and I input some numbers for X, say 1, 2, and 3. Okay. And let's say the data for Y is 1, 4, and 9. Okay.
Mm-hmm.
Now you'll probably recognize that as a very simple equation as Y equals X squared. Okay. And by default, graphical analysis will put X down here on the horizontal axis and Y on the vertical axis. Okay.
Mm-hmm.
All right. And and I think my picture's bad. The graphical analysis, I believe, puts it right here. Puts X here and y here. Okay. Now, let's say, and so this graph would kind of look like this. Let's say that I wanted to look at this graph, as I say, a simpler graph using a complex axis. So let's say I wanted to put y on the vertical axis still, but x squared on the horizontal axis. And if you do that, you'll get a straight line. So that was kind of my wording, that it's kind of a nice technique to learn in science and engineering, to take a complex graph with simple axes and then change that into a simple graph, but then complex axes. Okay, so what you got to do first is make that column that you want. So I would have to, in my table, make x squared. So that's where I'd go to, in graphical analysis, I'd go to data. I would go new calculated column. And when I go calculated, it gives me a little box that says formula, or actually it says equation, not formula. And then I can put in, the formula, which in this case would just be x caret 2. And it would make that column. So that'd become a 1, that'd become a 4, that'd become a 9. But then I think this gets to the heart of your question finally. Once you've made that column, click right on that which you want to change, which in this case, it's x. So click right on that. And then a dialog box will come up, or even just a small one, and say, okay, what is it that you want to plot on this x-axis? And then what will show up is all the options of all the columns you created. So you'll see one for x, one for y, and one for x squared. So that's why you have to make the x squared first. So you can select it once you click on it, because when you click on it, it'll give you the options of all the columns you have made.
Okay. I've been kind of following along with this and I think I'm doing it correctly.
Okay. And did you click on this X and see where it gives you this optional box that says, okay, what do you want to plot on the x-axis?
Yes. Yes, it did. So now
Okay.
my x-axis is the new calculated column.
Ah, okay.
All
So
right. Yeah, okay. I think that helped. I think the only thing at this point would be for that, I guess the y-axis column. Or which,
okay.
Yeah.
Yeah, and then the y-axis is the same logic. Let's say I wanted to plot something crazy on the y-axis, like x, y.
Okay.
Of course, first thing I got to do is go and make that column. So I'd go new calculated column and put in the formula, which in this case, I guess would be 1, 8, 27. Okay. So then if I wanted to plot that, I come over here and I click, back here, I click on the y-axis, and then it should give me a box, just like it did down here of, okay, what is it you want to plot on the y-axis? And then select, but it'll give you all these options. Select the one you want, which at this point in my picture, I would have 4 to pick from that I can plot on my y-axis.
Right. Okay, so I got the x-axis part. I guess the last one was just, do we use one of the columns from the data that we collect as the y-axis, or is it a new one that we use?
So now I'm gonna have to go back to the graph. Which graph is this?
This was the second one.
So is this the electric field one?
Yeah, for lab 2.
And so you're asked, I think on that one, to make a plot of the electric field versus R squared? Is that what you're struggling with?
I think it was either that or 1 over R squared.
Oh, yeah, yeah, I bet it's 1 over, yeah, 1 over R squared. Yes, yes, yes. Okay. All right. So, okay, good. So your original data should look like this. You should have R and E for the electric field.
Yes, or I think we had 3 different electric fields, which was just like the 3 different magnitudes of the
Oh.
charge.
Oh, good. Oh, yes, yes. Thank you. E1, E2, and E3.
Hmm.
Okay. Now, okay. And then you need to make a new calculated column that is 1 over R squared.
Okay.
See,
Yes.
because by default, cross this out, by default, the graphical analysis will plot E1 versus R.
Yes.
All right. So the two axes you need to change is, first of all, click on the R so you can select 1 over R squared. And then, oh, actually, even before that, because I think, oh, hang on. I think before that, don't they ask you to plot all 3, E1, E2, and E3 versus R first?
Yes, that part was all good.
Oh, okay. So
It was just
on
the
that-
last.
Okay, so if you got that one, then you already figured out how to make the y-axis do multiple plots.
Correct.
And that's, yeah, okay. And that's what I was about to explain. You just click on here and click more. And then instead of having individual selections, you can checkbox. And so you checkbox those.
Hmm.
Okay, so if you've already done that, then the next step is to click down here on the x-axis where it says R, and then just select 1 over R, and it will do that for all 3 of your plots.
Perfect.
So hopefully you'll have something that looks like that now.
Yeah, that got it. Thank you so much.
Okay. Okay, good. Nice.
All right.
Good. And glad you're catching up on a late lab. All right, good. So Brendan, excuse me for kind of jumping. I thought maybe that'd be a short one. I guess it was a little longer than I thought, but wanted to get him going on his graph here. And I know that some of these problems, I don't know if this is one of them, but some of the ones we do here in 122 can be super long. I'm sure you experienced that as you try to do the homework.
Oh yeah, definitely.
That's an understatement, huh? All right, so let's jump into chapter 28, number 7. And let me use my other screen here to find that problem. 28 number, oh, sorry, so I need to go back. Number 7. This is an interesting looking one. It says here, consider the circuit shown in figure 7. So let me just kind of draw it up here for partly for myself, but partly for anybody watching the video later on here. They call this EMF, 25 volts. Then there's a 10 ohm resistor. And it looks like that is put in parallel with another 10 ohm resistor. And that in parallel with a 5 ohm resistor. And then this whole grouping, which they call A to B, hooked up with a 5 ohm and a 20 ohm resistor. All right. So consider the circuit as shown. Find A. the current in the 20 ohm resistor, and then B, the potential difference between points A and B. All right, so I'm gonna grab some colored markers here. Get myself ready for that because we've got Kirchhoff's loop rules and the node rules going on here. I might make this a little bit simpler and do these two in series because the current looks like the current would probably come around this way and go to the 20 and then to the 25. So maybe I'll redraw this. In this kind of first step here. And say, that I have the 10 and the 5 and the other 10, and I'm just going to replace this with a 25. And so this is an equivalent circuit. And as you probably heard me say a few times, you know, equivalent circuits are really nice. We have to always remember they're not the original circuit. So usually the question is about the original circuit. So the equivalent circuit is only nice if it helps us get back to the information or the answer to the original circuit. And then sometimes the equivalence of the equivalence is nice. And I would say in this case, the 10, the 5, and the 25 are all in parallel. So now remember, in parallel, you can connect one side of them and equally connect the other side without going through another object. I say without going through another object or another element is because as I try to come over here to this other 10, I have to go across this battery, which would change the voltage. So the voltage across this 10 is not the same as across this 10. But the voltage across this 10 and this 5 and this 25 are. So these are all in parallel. And so maybe I will find the equivalent of these three. So I'll go 1 over 10 plus 1 over 5 plus 1 over 25. And so grabbing my calculator here, I'll take the 10 and the reciprocal of that. I will add it to the 5, reciprocal of that. And I will add it to the 25, the reciprocal of that. And then, of course, take the reciprocal to figure out what that equivalent is. So the equivalent of these three is 2.94. So let me draw, then if I call this page 1, let me draw page 2 on page 2 here. Now, actually, let me squeeze it in here on page 1. So this is going to get kind of long. I'll put the 25 volts here still and the 10. Haven't touched those. But in replace of those three, I am going to put 2.94. So I like to call this the equivalent of the equivalent, which, of course, this is the equivalent of the original. So let me call this the equivalent. Let me call this the equivalence of the equivalents. So two equivalents. And in fact, now you could even see, I don't know if I have to draw it, maybe I will. One more thing is these two, if you look at the equivalent of this one, this would be in series. And the current would come out here and go across. So looks like I can do the equivalent of the equivalent of the equivalents. And so third one, a third equivalent. And if I add those two together, I get 12.94 and 25 volts. All right. So keep in mind, back here on page 1, this is the original circuits. However, this is equivalent. This is also equivalent. And this is also the equivalent. So now begs the question, all right, how do we get to what we want to know, which is back here in the original circuit? And I believe it said, what is the current through this 20? Let me come back here. What does it say here? A, the current through the 20 ohm resistor. Okay. So this is really what they want to know. Now, if you look at this third equivalent one, it means very easily I could just apply Ohm's law, 25 volts divided by 12.94 ohms. So 25 divided by 12.94, and it looks like a 1.93 amps would be the currents coming out of this battery. 1.93 amps. Now, of course, remember, this is the equivalent, the third equivalent. So you have to kind of ask, how is this useful back in the original? Well, it means that that's what comes out of the battery, 1.93. But clearly, when it hits this node, some of it goes to the left, some of it goes down through the 5, and some of it goes to the right and through the 20. That's the stuff we want to know. So the current we're interested in is not this 1.93. It's a fraction of that that goes to the right. Okay. Well, so how does that help us? Well, again, usually maybe coming back a step from equivalence number 3 to equivalence number 2. So let me do that for a moment. This would be coming out of the battery 1.93 amps. And the reason I'm going to do that is because this 2.94 is, remember, the equivalent of these 3. So if I could figure out the voltage across this one, that would be the same as the voltage across either of these ones. And the one that would be interesting to me would be the 25, because the 25 is the equivalent of this 20 and this 5, which is ultimately my question that I'm trying to get to. So what I'm going to do here is equivalent number 2 is to say, what is this voltage? And so it would be
voltage on that one would be the same for the 10, the 5, and the 25 on the next one up, the first equivalent.
Yes.
Okay.
Yeah. Yep. And that what you just said is the reverse of how we got here. We went from here to here because we said they had the same voltage. We said they were in parallel. And so I'm going to take advantage of that, working backwards and saying, all right, I'm going to find this voltage because it will be the same as these 3 that you just said. All right, so let me get my calculator here and do that. I've already got the current still in my calculator, and then the resistance is the 2.94. And so that voltage would be 5.68. And then, as you said, let's apply that back up to here. And so that means the voltage across this 25 would be this amount, 5.68. And that would have to equal to the current that goes through this 25 and the resistance of that 25. And maybe now you can see where I'm going to get my answer, because once I calculate this, which is the current through this 25, I can look back to that being the same as the current that is in this whole loop, because this 20 and 25 came from the fact that I said they were in series. I said they had the same current. that's why I put them together. So if I could ever figure out what current is in this 25, I would get what current is in this 20, as well as what's in this 5. In fact, what's in this whole loop. But that's the answer I'm looking for, what's in the 20. So here is the answer to at least A. I'm going to take that voltage and divide it by the 25, and I get 0.227 amps. And that's the power of these equivalent circuits. And I know you guys saw it for the first time when we did capacitors. But I think it takes twice to really get the hang of how this can be useful. And basically the answer is you start with a complicated circuit and you start getting the equivalents, and then equivalent 2, and then equivalent 3, and however many you need to make it kind of a simple calculation. Then work backwards to get to the real circuit again. And so it's kind of work down and work back up and to find out what that current is. All right,
just
so
to be sure, series have the same current, parallel have the same voltage.
right.
Okay.
Right. And maybe I should just emphasize, since you brought it up that way, sometimes there's neither. And
Yeah.
those are harder problems. And that's why we have the Kirchhoffs loop rules, because they just use the fundamentals of conservation of energy and conservation of charge. And then we just write out a system of equations. And I would say that those are usually maybe a little harder to solve because we have a whole system of equations. We can't reduce it something small and work backwards. But on the other hand, if you use the matrix solution on your calculator, we're not really doing the math anyway. So we're letting the calculator do all the math. So maybe it's not so hard that way. And I could have done this with the Kirchhoffs laws, but in general, I think the equivalent ones are easier if the circuit will allow you to do it. So I guess I kind of always look that way. And this one, to be honest, when I started this, when I saw this, I'm like, ooh, this is not going to be equivalent. I'm going to have to do some Kirchhoffs loops. But as I started working through, it didn't come out that way. Now, that's the currents. Let's see. The next part of this then is what is the potential difference between A and B? Oh, and I guess I've really already done that because the A and B right here is on each side of the 20 and the 25. So the A and B would be right here, or however you want to put it. This would be the A and this would be the B, or this could be the B, this could be the A. They're all the same voltage on this side. And so the voltage across the three parallels. So whether you're talking about the 10 or the 5 or the 25, all of them have the same voltage, which we said was the 5.68. So that's the answer to B. In fact, we had to do B before we could get to A, at least doing this way. I suppose if we did the Kirchhoffs laws, we would have gotten A first and then used that to get B. But the way we did it with the equivalencies, we needed to actually get that voltage first. And I suppose I should check my answer here just in case I did something a little amiss. Let's see. Yeah, okay. He writes it in milliamps, 227 milliamps. Okay, so that's the same thing. And a voltage of, oh, and he did it the same way I did. So he actually found this first. So he actually, yeah, did the equivalencies and shows them there. Nice. All right, hope that helped.
Yeah, thank you.
All right, let's see. I'll come back over here to the little chat room. All right, I don't see another question here in the chat.
No one else has one. Can we do 21?
Yeah, absolutely. Yeah, no one else throw anything in the chat. So, all right, let's go to number 21 here. So chapter 28, number 21, and the time is 11:08. All right, so let's see what this one says here. Scroll down, number 21 says, oh, that's the wrong class. Sorry about that, went to the wrong tab. All right, let me try that again. All right. Here's here's an interesting one. And I wonder if we can do equivalence here. And again, my first thought is I don't think we can, and I kind of hope not, so that you can kind of see the other approach here. It says, consider the circuit shown in 21. What are the expected readings on the ideal ammeters and ideal voltmeters? All right, so let's see. I'm going to start maybe kind of in the middle of the circuit because it lists like two batteries. One is a 6-volt battery. The other is a 4.5-volt battery. Looks like the 6 volts is feeded into a 10 ohm resistor, and the 4.5 is fed into a 5 ohm resistor. These are then connected together. Then, interesting enough, across the top is a 6 ohm resistor, no battery. And across the bottom is another 6 ohm. Then they apply a voltmeter on the two positive terminals of the battery and an ammeter right here in the top branch. Okay. All right. Now, they ask for the readings in this, so I don't have to solve for everything. Although I might have to solve for everything to get there, but I think it might be good to maybe solve for everything, but maybe for starters, I'll just do this. That if you remember a loop, you add up around a loop. Maybe I'll do the simplest loop right here. That has to add up to 0 when you go all the way around a loop. And so this voltmeter, there would be a certain amount of voltage. And it could be plus or minus depending on how this is read. But why don't I just do this? I'm going to start down at this part in the loop, the lower, this would be the lower right-hand corner, and just go around this. I like this one because notice there's no currents that need to be considered. And here's what I mean by that. If I go in a clockwise direction, I go first across this battery, and the battery is either an increase or a decrease depending if you go from the small to the big or the big to the small. And so I'm just going to go from the small to the big, so it's plus 4.5 volts. It has nothing to do with the currents. So that's the neat thing about a battery. They have the same voltage regardless of what the current is. Whereas a resistor, the voltage change depends on the current. And I don't know any currents in this one. So I would, it's not as helpful if I go across the resistor. Now, as I go across the voltmeter from here to here, this is the reading on the voltmeter. Let me call this the plus side of the voltmeter. So the voltmeter would give me a positive reading if this over here was greater than that one. It would give me a negative reading if it was the other way around. So I'm just going to put plus V. That's what that means here. That is the reading on the voltmeter. That's the change in voltage. That's what a voltmeter reads. And I think that's part of the problem is what is a voltmeter really doing? And a voltmeter is really taking the voltage at the plus and then subtracting the voltage at the minus. And so it's that difference, it's that change. And that's what I put in my equation of my loop. So I'm going to put the V.
And how do you know which side is positive and negative?
Yeah, we don't on this problem.
Okay.
If you actually hold one in your hand, there's a mark on it that says plus, and it's also color coded red. So,
So it's basically just pick a direction, and I should
yeah. So
depending on the math.
yeah, I think so. So in reality, the way they gave us the problem, I can only tell you plus or minus.
Okay.
So if I took a voltmeter in my hand and put the red connection here and the black connection here, I would get a reading. If I switched them around, I would get the same reading, but a negative. So I'm going to treat this as if the person hooking it up hooked the red one up here and the black one down here. Do I know that? No, I don't know that, although it is kind of standard convention when you're drawing these circuits to make things of higher voltage higher up on the circuit. It doesn't always work that way. And it doesn't have to be. So I really don't know if this is a higher voltage than that one. But it seems like it's going to be. So it seems like this is going to come out to be a positive number. So like a capacitor, we say the voltage across the capacitor, and we usually say something like, hey, the voltage is 5 volts. Well, 5 volts, what we mean by that is if you go from the negative plate to the positive plate, you increase by plus 5. But if you go from the positive plate to the negative plate, you decrease by 5. So we tend to talk about absolute numbers, and that's kind of what I'm doing here. All right. Continuing on around this loop, the big line to the small line would be a decrease of 6 volts. And then I get back where I started. And so the sum of all the voltages changes should be 0. And so if I solve this math of a 6 minus a 4.5, which leaves me with a 1.5. So that's kind of the first step and the easiest step of this loop. And I'll say it again, my meter would actually say 1.5 if I hooked the red one up here. If I hooked it the other way around, it would say negative 1.5. And, which either one would tell me which one's the higher voltage. Because if I get a positive number, then I know where my red one is connected is the higher voltage. If I get a negative number on my meter, then the black wire is the higher voltage. And so it's standard practice for me. Often I don't care about whether I have a black wire or a red wire. I just hook it up and say, okay, hook one here, one here. And then once I hook the red and the black, and then I look at the meter. And the meter says, positive or negative, I pay attention to that, and I pay attention to the number. And so the number and the sign tell me, the sign tells me which one's the higher potential, and the value of it is just the absolute value. All right, so that would be my first step to get, okay, what does the voltmeter say? Now, the other part of this would be to do the currents. And here I'm kind of debating if I should do an equivalent, because I can't do an equivalent very far. I can do it a little bit. So maybe I'll do a little bit, but that I think almost makes it harder. I don't know if you can see that the 6 and this 6 are actually in parallel with each other. You kind of connect the left side of this 6. You'll see it's connected to the left side of the 5, the left side of the 10, and also connected to the left side of the other 6 with nothing in between if, this is why they use that phrase, ideal ammeter. Because if it's an ideal ammeter, there's no voltage change. So this would be the same as just directly connected to the left. Now,
Couldn't we just do the top loop the whole way, just the same way we did for the previous one? Like how the rectangle on the top, just work the way around the loop like that?
yeah, okay. And see, that's what I'm debating, which would be better to show you. I didn't, and so I'm gonna not do any equivalent. But what I am trying to point out is that you could do a little bit, because the 6 on the bottom and the 6 on the top can be combined together because they're actually in parallel. But you can't put the 10 and the 5 together. They are not in parallel with themselves. They are not in parallel with the 6. They are not in series. They're one of those cases I was trying to say you sometimes have neither. Here's what I'm saying by that. If I were to redraw an equivalent circuit, I would take my 6 volts and the 10 ohm, that branch, and leave it alone. I would take the 4.5 volt and the 5 ohm and leave it alone. But the top branch and the bottom branch, I would combine together. And it doesn't matter if I put it on top or bottom. Just because I had more space on the bottom, I drew it on the bottom. And the equivalent of 1/6 plus 1/6 is 2/6, which is 1/3. This would be 3 ohms. So you could say that start with this circuit and then get the equivalent. However, you're still stuck at this point, because notice that the 10 and the 5 and the 3 are not in parallel. They are not in series. They're neither. And so we need to do some Kirchhoffs loops and node rules. And I'll say they're not because watch, if I take the left-hand side of the 3, which is also connected to the left-hand side of the 5, which is also connected to the left-hand side of the 10. So that's looking like they might be in parallel. Watch what happens when I do the right-hand side. I can't get to the right-hand side of the 5 without going through another circuit element. That would change the voltage, which means the voltage across the 5 would not be the same as the 3. And likewise, the same problem happens up here. I can't get to the right-hand side of the 10 without crossing this battery, which changes the voltage. So the voltage would change. And so the voltage across the 3 would not be the same as across the 10. So these 3, which, drawn like this, kind of look like a parallel drawing, but they're not what in electronics we would call parallel. They're not parallel. They don't have the same voltage, and they're definitely not series. You can't go from here and then go into the 5 without hitting a node. You do hit a node right there, and so the current kind of deviates at some node. So there's node in between. So it's not series and it's not parallel. Which brings me to this question in my mind, as I still haven't answered yet. Should I just do the loops back on the original? And part of me says yes, because what's the point of making this equivalent? It's not very equivalent. There is a small thing to gain, because if you look at here, there would be 4 different currents through each branch. 1, 2, 3, 4. So I would have 4 equations with 4 unknowns, whereas this would only be 3 equations with 3 unknowns. And I would much rather solve a problem with 3 unknowns. So part of me thinks, well, maybe I should do this one. On the other hand, I'm not going to really solve it. I'm going to put it into my calculator. So do I really care if I've got 3 equations versus 4 equations? So maybe I'll just make a decision and say, no, I really don't care about this. Not a bad idea. But I have no problem with making 4 equations and 4 unknowns because I'm going to put them into my calculator. And I got to do that anyways, 3 equations, 3 unknowns. And then once I do that, I have to work backwards from this equivalent back to the original to find out what the current is to the ammeter anyways. So that's why I'm going to say, you know what? Even though 3 unknowns is more tempting than 4 unknowns, I still have to work backwards and just forget about this. All right. So with that in mind, let me, now that I've drawn on it so much, maybe I'll just redraw. So here's the top piece of 6 ohms. Here is the 6 volts branch with the 10 ohms. Here's the 4.5 volts with the 5 ohms. And here is the 6 ohm down below. All right. So redrawing this circuit. Let's see what we have here. Maybe I will say what is coming out of this battery, I'm going to call current number 1. And what comes out of this battery, I will call current number 2. All right. Now, I'm not sure exactly what happens at these nodes yet. We'll talk about it. But I do know that it's going to come across and then split, and some of it's going to go up. So let's talk about the stuff that goes over the top here as current number 3. And that would be what we're looking for, because this problem said find the current through the ammeter. And the ammeter is up here at top. Maybe I should put it in my drawing here. Here's the ammeter. So that's really the one I'm interested in, is number 3. But here's what could happen, and I don't know which way it happens. I don't know if number 1 splits, and so number 3 is less than number 1, and then so some of number 1 goes down this way and combined with number 2, which flows across here. Or does number 2 come in and split so that some of it goes down? So the current down here, which maybe I'll call this current number 4. Maybe current number 4 is less than number 2. So that means number 2 goes this way. And if that's the case, then it would combine with number 1. And so coming across the top, number 3 would be greater than number 1. So I really don't know what happens here. But so what? I'm interested really not in this area. I'm interested in the current going through these resistors. And so 1, 2, 3, and 4. And here's what I do know. The stuff that comes in, 1 and 2, somehow recombines and comes out. So current number 1 plus current number 2 recombined. And again, I don't know if current number 1 splits off and joins up with number 2, so number 4 is greater than number 2, or the other way around, current number 2 splits and goes up, combining with number 1, so number 3 is greater than number 1. I don't know which one, but I do know this. I do know that everything goes in, recombined, and comes out. So current number 1 plus current number 2 has to equal current number 3 plus current number 4. So that much I do know. That is Kirchhoff's node rule. I think your book, I can't remember if they call that number 1 or number 2. I think it's number 1. And it's a conservation of charge. It just says, okay, you have a situation here where they come in. In this case, what happens right here, don't really know and don't really care. But I know it comes out. So what goes in equals what comes out. All right. So I will refer to this perhaps as equation number 1. Now, remember, I need 4 independent equations. And I don't know if I made this very clear in the video. I'll keep saying it when I can. The math tells us if you have 4 unknowns, you need 4 independent equations. And Kirchhoff's loops, if you do the small loops, you will always have independent equations. If you do, let's say, a small loop, let's say I do all small loops. So I do the top, the middle, and the bottom. But then I decided to do the big one. That big one would not be independent of the other 3. Mathematically, the big one would be the same as if I just mathematically combined the top, the middle, and the bottom. So where students can get themselves into some troubles is they realize that they need 4 equations and they try to do all 4 of them with just loops. And the problem with that is there's only 3 independent loops. And that's why this equation, the number 1 equation, is really so important. It is the way to get that 4th equation. I know I called it number 1, but I'm looking at this going, okay, I got 3 independent equations from doing the loops. So that means I need at least 1 from the nodes. And that's the best way to do it, I think, is to just do the small loops. You know, they're always independent. Okay. All right. So with that in mind, let me now do the top loop and then the middle loop and then the bottom. All right. So doing the bottom, or excuse me, the top loop, maybe I'll start here in the lower left and just go around in a clockwise direction. All right. So adding up the voltages, I would go from little to big. And so that is plus 6. And so this is kind of like we did earlier on, that it doesn't matter what direction the current is going. For a battery, it's if you go from little to big, it's an increase. If you go from big to little, it's a decrease. And so when we say a battery is 4.5, we mean it could be a plus 4.5 or a minus 4.5, depending which way you go. It's the same thing we were talking about the voltmeter with the red and black wires, or the capacitor with the positive and negative charges. But in this case, starting over here on the lower left and going clockwise, I would go from small to big. So that'd be an increase of 6. So that's why I put a plus 6. And then over here, I'd go in the direction of the current that I indicated. So that's a decrease. So it's a minus. And it would be Ohm's law, resistance times current. So the resistance is known as 10, and the current is what I labeled as I1. Continuing on around, and again, ideal amp meter. So I don't have to say that has any kind of resistance. In reality, it probably has a couple of ohms of resistance. All right, but treating it as a non-resistor, I could get here. And again, I'm going with current number 3. So I'm going with the current, so it's minus. The resistance is 6, and that's I3. And then I'd get back where I started. So I guess I'll call that equation number 2. That's my top loop. Well, why don't I do the bottom loop? And I'll do the same pattern, starting in the bottom left and going clockwise. But let me emphasize, it does not matter where you start, and it does not matter which direction you go. Just when you go around a loop, all the voltages add up to be 0. All right. So just because I'm starting in the lower left doesn't mean you have to. And just because I'm going clockwise doesn't mean you have to. All right. So I'll start here and say, okay, little line to big line. So that's a plus 4.5. Then I get to this resistor and I'm going with the current. So it's minus. The resistance is 5 and the current is I2. Continuing on, here's the part that I was saying. I don't know which way the current is going. And fortunately, there's no resistor, because when I put a plus or a minus with a resistor, I need to know which way the current is going. I need to indicate it. And I don't need to know that. And I don't know it. So it's a good thing I don't need it, because I don't know it. So I'll just keep going around. And as I come across here, here's the 10. But notice I'm going against current number 1. So that's where a plus would come. And it would be 10 times I1. And then I would get to this 6-volt battery, and I'd go from big line to little line. So that's a decrease, minus 6 volts. And then I keep going along a wire, and there's no change in voltage in a wire. And I get back where I started. So that's the whole loop. So you add up all the voltages changes, you get 0. And that's our middle loop. All right, finally now, let's do the last loop. And I'm debating if I should keep going or change my direction and my starting point just to show you it can be different. Maybe I will do just to show you it can be different. So I'll go exactly opposite. How about over here? So instead of starting in the lower left, I'm going to start in the, oh, this is lower right. I think I got my right and left mixed up. Sorry about that. So those two I started in the lower right. So now I'll come over here and start in the upper left. All right, so starting in the upper left, and this time I'll go counterclockwise. Why not? All right, so I'll start here, go along a wire. Along a wire, no change in voltage. This is my first change in voltage. And I'm going with current number 4 as labeled. So I would say minus 6I4. Keep going around, through a wire, I get to a battery. And I'm going from little to big, so that's a plus 4.5 volts. Then one more resistor before I get back where I started, and that's with the current, so that would be a minus. And it would be a 5 times I2, and that equals 0. And so that's equation number 4. So there you have it. I did the top loop, the middle loop, and the bottom loop. I'll say it again, doesn't matter where you start and which way you go. And then, of course, I need at least one other information, and that was my thinking that the currents that flow in equal the currents that flow out. So here are my 4 equations, 4 independent equations, and probably best to set this up like a matrix. So 1, 2, 3, 4. And so current 1, current 2, current 3, current 4 equals. All right, so let's take these 4 linear independent equations and write them as one matrix equation. All right, so starting with this first one, let me imagine moving the current number 3 and the current number 4 to that side. So what I would have is a coefficient of 1 in front of current number 1, a coefficient of 1 in number 2, a coefficient of -1 in front of 3, and a -1 in front of 4. And so if you remember your matrix multiplication, that's how this can represent equation number one, because you take this first row and multiply it by this column. So you get 1 times I1, 1 times I2, minus 1 times I3, and minus 1 times I4, all equal. And in this case, once you move everything over, there's nothing left on this side, so it equals 0. So this row and this column equaling 0 represents equation number one. And so that's how we're going to combine and make these 4 linear equations into one matrix equation. All right, let's look at equation number 2. It looks like equation number 2, this would be current number 1 has a coefficient of -10. So -10 times I1, nothing for I2. There's no I2 in here, so 0 is a coefficient for I2. -6 is the coefficient for I3, and 0 is the coefficient for I4, because there's no I4 or I2 for that matter. And so that would be everything on this side. But I got to imagine moving the 6 over to here, so all that equals -6. So this second row, first column, multiplied together equaling -6 would be a mathematical equivalent of equation number 2. Now equation number 3, the same thing. There is a plus 10 for number 1, a minus 5 for the coefficient in number 2, a no I3 and a no I4. Because that would be, if you multiplied this third row times this first column, that would be 10 I1 minus 5 I2, no I3, no I4 equals, and so if you imagine putting this 4.5 and -6 together, that'd be a -1.5, and then moving it to the other side would be a plus 1.5. So this third row, first column would be equation number 3. And then finally, equation number 4 would have no I1, -5 I2, no I3, -6 for I4, and then imagine then moving that to the other side to be -4.5. So that's how I would write mathematically 4 independent linear equations as one matrix equation. And fortunately, our calculator can do a lot of what we call matrix manipulation and get this to look like one zero 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 0 1 0 0 0 0 1 0 0 0 0 1. And if you can manipulate this matrix around, and again, fortunately, we're not going to have to do it, but if you can get this front matrix, whatever you have to multiply it for, and of course, whatever you do to the left, you have to do to the right. So whatever the calculator does to change this matrix into this matrix, it's going to do the same thing on this side, and it's going to get some numbers here. I'll just call them A, B, C, and D. And when you get it in this form, which is called reduced row echelon form, you can see then that this first equation would just be I1, no I2, no I3, no I4 equals A. So whatever number is right here in my matrix is the value of I1. And then you can see it here too for number 2. This would go 0 times I1, 1 times I2, 0 times I3, and 0 times I4. And that would have to equal B. So that would tell me B is number 2. And then the same thing, C would have to be equal to number 3, current in number 3, and D would have to be the current in number 4. And of course, what we're after is right here, C. What is the current in that top piece. Of course, we did much more than that. We're now going to get the current everywhere. In fact, we can even answer this question. I'm kind of curious about this question about which way the current was actually flowing here. So maybe I'll add that into the mix here before we finish here. All right, so on my calculator, and what do I have? Which model is this? Is this the 84? Yeah, so the TI-84. I enter my matrices with a little menu here that's called the matrix. I don't like it being behind the second key on the 84. I think they do a better job on the 83. You don't have to hit the second key, but it's not that big of a deal. And I know there's like the Casio ones, and those are probably the most popular ones, the TIs and Casios. But whatever calculator you have, let me encourage you to figure out how to make a matrix and then have the calculator do a process called reduced row echelon form. Okay, so in my case, I'm going to come over here and edit. I'm going to go to the edit menu. I'm going to go A and just select my matrix A. Now it looks like I already have a 3x4 saved in here, but what I'm going to want is a 4x5. I'm going to want to enter this front matrix, which is 4x4, and the last piece right here is the fifth column. So I will need a 4x5 matrix. So I'm going to go enter, and the first thing it asks me for is how big. And so I'm going to go 4, enter, 5, enter. And then it says, okay, so this is your new matrix A. It is a 4x5 matrix. Enter in the values. So I will go 1, enter, and it just moves over to the next one. 1, enter, and moves over. -1, enter, and it moves over. -1, enter, and then it gets to this last one, 0, enter. And on my calculator, you can only see 3 columns. If I scroll over, here's the 4th and here's the 5th. So I've entered across the top a 1, a 1, a -1, scroll over 1, and scroll over again 0. And now it'll take me back to the start of row 2. So that would be a -10, enter, 0, enter, -6, enter, 0, enter, and -6, enter. And so that would be my second row, and then mine automatically goes down to the third row. Okay. So a +10, enter, -5, enter, 0, enter, 0, enter, 1.5, enter, and then 0, enter, -5, enter, 0, enter, -6, enter, and then finally -4.5, enter, and then it just stays right there. All right, now I suppose just to kind of check, do I have this column 0, -6, 1.5, 4, -4.7? That looks good. Let me try this column, -6, 0, 0, 1, -1, good. Let me try this column, -1, -6, 0, 0, good. Let me go one over, -5, -5, 0, 1, good. And over here, 1, -10, 10, and 0. All right, so just checking to make sure that I had entered all those values correctly. It's like I've got my matrix A now. Mentally, I just like to clear it. Okay, so I've saved my matrix A. Let me go back to the matrix menu. You can see here that, name matrix A has a 4x5 matrix in it. So that's one I just saved. Let me go then to the operation I want to do on that matrix A. It's called the math operation. So I'll go to the math menu and scroll down. Doesn't show up for a little bit. There it is, RREF. So this is the fancy mathematical operation. It's kind of like, saying I'm taking the sine of the number 7. Instead, I'm taking the RREF of matrix A. So if I just hit enter, you'll see in my calculator, it put RREF with an open parenthesis, just like if I would have hit sine. Let me not do it now, but I would have seen sine with an open parenthesis, sine of what? And it would need a number. This is RREF, and then it needs a matrix. So I need to put a matrix. So I'll go back to my matrix menu under names and just select A. And it, by default, number one's already selected. So I'll just go enter. See, so it says RREF of matrix A. And you can choose to close it or not. The TI doesn't make you close it. Probably is not good. I know if you're writing computer code, you don't close it, you get all kinds of syntax errors there. But I'll just close it for completeness and then let the calculator do its thing. As I said, now when I hit enter, it's going to manipulate this around to get this. And whatever it does to the left-hand side, it's going to do to the right-hand side. So these right-hand side, these numbers are going to change. There are going to be some new numbers here. But these are good numbers to have because these are the answers. A is current 1, B is current 2, C is what we're looking for, current 3, and D. So I'll just take my calculator and hit enter, and it will do its mathematics. And there's the first part of the matrix. There is the identity matrix, the 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. And then this would be the A, B, C, and D. And I can write down those numbers. Maybe I'll squeeze it on this one page. So this is equal, and I get 0.363, 0.426, 0.395, and 0.395. Now, of course, my answer that I want is, of course, C right here. But the thing to mention probably is that D is the same as C. And if you go back to your original circuit, that's not a surprise because these two 6s are in parallel with each other. So they have the same voltage. And because they have the same resistance, they must have the same current. So it doesn't surprise me at all that they have the same current. So 3 and 4, the same current is a very good sign. It also then helps me with another curious question right here with, I guess this is number 1. Number 1 came out with this current, 1.36. And did it split off and go down so that less went up? Or was it joined up with some coming up and have more going up? Well, let's go to number 3 down here. Number 3 is a little bit more than number 1. So that would tell me the current is going up. Which would then tell me it's number 2 that comes and splits. Some goes up, most of it goes down. And so number 4 should be a little less than number 2. So number 4, a little less than number 2, right? And so there I have a better, I think, understanding of what's going on now in this circuit now that I've solved for all the currents, even though they only asked for that. Hope I didn't talk too much. Wow, I talked a lot, way past our closing time. But let me check the answer. Or I guess I should say our break time. Let's see, what did I do here? Number was this again? 21 here. So they got 0.395, good. And they got a voltage reading, if you remember all the way back on that first step, of 1.5, there it is, 1.5. And then I had them plus there, but I threw a minus there to say it wouldn't really matter. They have a plus there. Nice. All right. Well, hope I wasn't too long-winded, but it was nice to kind of see the circuit in action and actually put all those pieces together. Hope that helped. Did that help, guys?
Yeah, thank you.
Any more
just a real
questions?
quick thing.
Yeah.
Remember the lecture when you did this, one of the values was like some number, but then on the side, it was actually like e to a power. I typed it on my calculator and it actually would not let me scroll over to see that value. So I'm not sure. I don't know if there's like, some trick or something. Because you have the 82.
Yeah. Well, let me come back to this. You're right that if you look at my answer here, I can't see the end of my matrix. So I should be a little concerned that there might be a big number here and then have an E, which represents 10 to some power. Now, the reason I didn't do it for this problem is it would only show up that way if there was like a number and then a decimal place. So
Yeah.
you would never write it. When you write in scientific notation, you always put a first number and then a point. And it didn't do that. So I know this is not an E times something. Okay. However, to scroll over, at least on my calculator, you just arrow over.
Huh. I tried
you
to
can-
do that and it wouldn't let me for some reason.
Yeah. So I don't know what model you have. It must be different than mine.
It's weird. I have the 84 too.
Oh,
I don't
well,
know.
try it again. Maybe you already hit something, and then once if I hit something, it won't let me scroll over anymore.
Oh, okay. Yeah, I'll look into it more.
And I can go up and do something like this and select the whole thing and hit enter again. Oh, maybe I can't. Oh, yeah, well, yeah. See, now I'm stuck. I can't go over
Okay.
anymore.
That might have been what happened then. I don't know.
Yeah. I would encourage you to give it a try. And it could be yours is different. I have had that. My TI-84 is a little different than other TI-84s. Like I have two 84s, and one of them must have a better screen or something, because when I do something like a square, this is the better one. It gives me a little a 2 that is kind of a smaller font, but my other one, it doesn't give me a smaller font. Kind of weird looking. Yeah, like if I did something like that. Yeah, see this one's got a better screen than my other one. So there is a little differences between some of the 84s. I don't know how to recognize the difference. They don't really say anything. This does say 84 plus, but even the plus I've come across that the screens are just different.
That's weird.
Yeah, it is weird. All right. Hey, well, long-winded as usual. Looks like I'm 25 minutes over. I'll let you guys take a break. I'll take a little break and I'll come back at 12:30 and we can work on some more if you guys like.
Cool. Thank you.
All right, guys.